Okay, so the master method, briefly, is kind of a cookbook formula. It works on many but not all recurrences, and it's basically based on matching a case in the master theorem. So as we'll see shortly, the master theorem kind of breaks down into 3 distinct cases, and each one has basic rules for matching that case and some restrictions on when it may not apply. The master theorem describes recurrences of this form, t of n equals a times t of n over b plus f of n. So this is very comparable to the forms that we've looked at so far. Just like before, a represents the number of recursive calls, and b controls the size of the subproblem. And finally, f of n is the work done other than recursion, the work on recursion itself. Okay, so let's go ahead and look at the master theorem. Okay, so the master theorem largely describes algorithms that fit into a category called divide and conquer algorithms, or they have the divide and conquer pattern. So the typical approach here is that they divide a problem into smaller parts, and they solve those smaller parts. That would be the part of the conquering thing. And then they combine the solution to the smaller parts together to come up with an overall solution. So that also kind of fall into the part that's referred to as conquering the problem. So we've already seen an example of this. Binary search can be thought of as a divide and conquer problem. So it divides the problem into one smaller part that's roughly half the size, and then it solves the smaller part. In this case, it continues the search in the smaller part and eventually returns the solution from the smaller part, which is either the index of the item it was searching for or an indicator that it wasn't found. Okay, so we can also think about this in terms of kind of general pseudocode. So the pseudocode that we'll look at now is from the Wikipedia article, specifically on the master theorem for algorithm analysis. So the basic idea is that you'll have some generic procedure or method, and it works on some input of size n. And if n is less than some constant, it will solve the problem directly without recursion. Otherwise, it will create subproblems of x, each of having a specific size n over b, and it will call the procedure p recursively on each of those subproblems. Okay. It'll then combine the results from the subproblems together. So again, this is kind of this conquering part of the problem. So we can actually develop a recurrence equation for this that would look something like this. So we would have a recursive instances of the problem, and each one of those would take our n and divide it by some b, making it into a smaller subinstance of a problem. And of course, we have the amount of work that's done at each instance that isn't being done by the recursion. Okay, so let's analyze equations of this form using the recursion trees that we've already been looking at and using as a tool for kind of our accounting-based approach to coming up with a closed form solution. So consider one of the examples that we've already looked at, t of n equals t of n over 2 plus c times n. So for this, we can figure out what our constants are for this new and improved form of equation. So a, for this example, would be 1. So that's, again, our multiplier on the number of different times the function is recursively called to solve an instance. And our b will be 2. We're cutting the problem in half each time we recur. So let's look at another example problem. T of n equals 2 times t of n over 2 plus c of n. So here we see that we actually have a multiplier. There are multiple recursive calls going on here. And we can also see that the amount of work that we do at each node, at each instance, depends on the problem size at that time. Okay, so just like before, we can figure out what our a and our b parameters are. So our recursion tree looks something like this. So you'll note that each node is doing c times the amount of work at that node. So c times n in the root node, and its 2 children each have divided the problem in half, n over 2, so c times n over 2 for each of them, and so on through the grandchildren of the root, and so on and so forth. Let's consider a slight variation of this problem. So let's consider what happens if we simply change that last parameter. So we still have 2 times t of n over 2, but here we just have plus c. So if you remember in the previous example, it was plus c times n. So in this case, our tree diagram looks a little bit simpler. So at each node, we do c units of work, and it no longer depends on the problem size. Okay, so just like before, we have a equals to 2, and b also is equal to 2. Let's consider one more variation on this. So in this variation, we will again just change that last component, the amount of work that we're doing at each node, and be c times n to the 5th power. Okay, so just like before, we could use our counting method and draw out our full recursion tree. So at the root node, we're doing c times n to the 5th units of work, or spending that much time, however you want to think about it. At its left child, we'll be doing n over 2 to the power of 5 times c, and the same amount of work at its right child, and so on and so forth. Okay, so in these 3 different examples, the thing that was really being changed was the f of n function. And in those 3 examples, we had c, a constant amount of work, c times n, and c times n to the 5th. Okay, this actually brings up our 3 major cases, or 3 major considerations of the total amount of time spent. Okay, so it is possible that the work we spend at each individual node, that f of n function, dominates the total amount of time. And we're always interested in limits, so the thing that dominates is really what we're interested in. So that's one option. Another option is that the work done at the nodes and the work to divide and do the recursion is balanced out. So that means there's roughly an equal amount of time spent in the f of n function as there is in the process of actually dividing the problem up into smaller pieces. So that's option number 2. Option number 3 is that the work of dividing and recurring actually dominates the total runtime. So that would be the time spent on a times t of b over n. Okay, so the Master Theorem is really about these 3 different cases and applying them to solve problems. Okay, so let's look at the first of these cases. That's where the work that's being done at each individual instance or node dominates the overall amount of time taken. So all 3 of these approaches depend on something called the critical factor. So the critical factor is a constant that we can get from log base b of a. And if you forgot your logarithms, basically you could convert to a arbitrary base by dividing using another log. So log of a over log of b gives us the log base b of a. Okay, so this critical factor can actually be thought of as the log of the number of subproblems divided by the log of the relative size of the problem. So it gives us some way of kind of understanding the problem growth versus the amount of effort it takes to solve an individual subproblem. Okay, so for case number 1, where the work at the nodes dominates, we will evaluate our f of n function, the amount of work being done at each node, and if it falls into n to the power of c, where c is less than this critical number, then we have our first case here, and we can say that t of n is in theta of n to the power of that critical number. Okay, so let's work through an example. So imagine that we've got t of n equal to 9 times t of n over 3 plus n. So we can identify the components of our equation. We've got our a is 9, our b is 3, and our f of n is just n. Okay, so now that we know that f of n is just n, we could also think of that as being n to the 1st power. Okay, so we could say that f of n is in the big O of n to the first power. At this point, we need to think about our critical number. So let's, we now know that we've got, we could kind of think of this as a coefficient c equal to 1. So c is 1. We've identified our a as 9 and our b as 3. So computing our critical number, it's log of 9 over log of 3, which is 2. Okay, so our goal here is to have to see if we match this pattern, to see if f is in the big O of n to the power of c, where c is less than this critical number. So we've matched that pattern. F of n is just n, which we can think of as n to the first power, so that would define our c. So c equals 1, and we've identified our critical number based on the log of a over the log of b, which is 2, so 1 is less than 2. Okay, so we've kind of matched our criteria here, and we can say that t of n is in theta of n to the power of our critical number, which again is 2. So we can say that this recurrence is theta of n squared. Okay, let's try a second example. So a slightly different recurrence, t of n equals t of 2/3 n plus 1. So let's go ahead and identify our parameters. So a is the multiplier in t, so that's going to be 1. B is how much the problem size gets divided down. We have to be a little bit careful here. So the problem size is going to 2/3 the original problem size. B is really just the denominator of this, so we'll have to actually take the reciprocal of this. So B will be 3/2. Okay, and finally our function f of n is going to be 1. Okay, so let's identify our critical number. So our critical number is it's going to be the log of a over the log of b. So log of 1 over the log of 3/2. So the log of 1 is 0, so this goes 0. Okay, and just like before, we should probably identify our f function to see how this fits in with the case that we've already seen of the Master Theorem. So if you remember, the case that we've already seen with the Master Theorem was about f of n being equal to n to some power c. Something like this, where c was less than this critical number. Okay, so kind of fitting in our pattern here, our function here is just 1. So n to the 0th power would be 1. So I guess if we pick a c to be 0, we're in O of n to the power of c. I guess we kind of fit that pattern. And our critical number is also 0. So we've got c less than or equal to c critical. I'm sorry. C less than C critical, and C must be 0, and C critical is also 0. That's not strictly less than, so we're not quite fitting this pattern. So this takes us to case number 2 of the Master Theorem. So case number 2 occurs when work at nodes is roughly equal to the work to divide and conquer, so when they're balanced. So in this case, the critical factor is equal to log base b of a again, so that's how we define the critical factor. And if our function f of n is theta n to the critical factor times log of n to the kth power for some k greater than 0, we fit this pattern. And if we fit this pattern, then our complexity is n to the critical factor times log base n to the power of k plus 1. So notice that you increase the exponent on log. Okay, so let's go ahead and analyze our second example here using the second case, and let's see if this is an appropriate fit. So just like before, we still have t of n is equal to t of 2/3 n plus 1. So again, we've already defined all of our factors on this. We've got a equals 1, b equals 3/2, and our f of n is 1. Okay, and we had already identified our critical factor as 0. Okay, so let's try and fit this into the form that we see over here on the right, and then try and identify what our k would be if it fits this form correctly. Okay, so again, f of n is equal to 1. So to fit this form over here, so we'd have n to our critical factor times, which would give us 1 since our critical factor is 0, times log base n, log n of k. Gosh, so we'd have 1, and we want to know what k needs to be. Well, just to get a constant 1, this could be a 0, right? So if we take the log of anything to the 0th power, we get 1. So k could just be 0. Okay, so when k is 0, the f of n is theta of 1, constant time. Okay, so we can now fill that back in. So it looks like we do match our pattern here. So our complexity will be based on the equation here. T of n is theta n to the critical factor times log n of k plus 1. So our k is 0, so k plus 1 is 1. So kind of just filling in the constants there. We'll start off with a big definition there. We'd already identified our critical factor was 0, and we identified that k is also 0, so k plus 1 is 1. So we end up being in the theta of n to the 0th times log n of to the 1st. So simplifying that down, n to the 0 is a 1. So we just end up with a theta of log n. Okay, so the second case is when our complexity of our f function is essentially equal to that critical factor. Okay, let's move on to one more example. So in this case, we've got t of n equals 3 times t of n over 4 plus n log n. So notice that our function f here is a little bit more complicated, and our parameters a and b are 3 and 4 respectively. So our function of f, the amount of time we spend at each individual instance of the problem, is n log n. We can again compute our critical factor by taking the log of a and dividing it by the log of b, and we come up with 0.793. Okay, using our previous approaches, we would have the f of n, and we'd identify kind of its coefficient, its c, and we'd come up with 1. And here we have c being greater than that critical factor. So this is our third case, and it isn't covered by the other two. The first case we looked at was when c was less than the critical factor. The second case is when they're equal, and here we have when c is greater than that critical factor. Okay, so this is our third case where the work of subdividing the problem dominates the overall runtime. It takes more time to work on the process of dividing the problem than it does the work at any individual instance. Okay, so for our third case here, we'll say that f is in omega of n to the c power. If we have c greater than our critical factor, and also we have some restrictions on kind of the overall growth of this problem, that it has to be bounded. So if a times our function of n over b is less than or equal to k times f of n for some k less than 1 and a large n. Again, we're mainly interested in asymptotic behavior and limits. So if that condition is met, we say that our overall complexity is in theta of f of n. Okay, so returning to our example and our definition for our third case here. So our third case is about our f of n being a particular omega of n to the power of c, where we've got two additional conditions met. If our c coefficient is greater than our critical factor, and also there's some limits on the overall growth of the subinstances of the problem. Okay, so if that's true, then we know that the f of n is our theta function, big theta. Okay, so again, we're looking at this particular recurrence, 3 times t of n over 4 plus n log n. So we've identified a is 3, b is 4, our f of n function is n log n. And we had already identified that our critical factor is 0.793, and our c coefficient appears to be 1. So that would be greater than our critical coefficient here, our critical factor. So we definitely don't fall into either of our previous two cases. It's not less than our critical factor, nor is it equal to it. Okay, so we may be in this case, but we still have to identify this other condition and see if we meet it. So we can start filling in our coefficients, and we'll still have this unknown k to deal with. So 3 times n over 4 log of n over 4. So again, we're worried about our f of n, but we're substituting in our subinstance size, n over b. So that's where this came from. And we're checking to see if it's less than or equal to k times our f of n function, n times log n. Okay, so in this particular case, all we have to do is come up with some coefficient k less than 1, or we can say that for suitably large values of n, this will hold true. So in this case, gosh, it looks like we've got 3/4 n times log of n over 4. Well, log of n over 4 will be less than log of n. Okay, so we could just pick a k of 3/4, and this equation will be true for all large n. Okay, based on that, we meet both parts of our conditions here. So c would be greater than our critical factor, and our other equation here is also satisfied. So we can actually make this claim that t of n is in theta of f of n, where f of n is n log n. So simpler stated, we can say that this recurrence is in theta, big theta of n log n. Okay, and so with that, we've kind of summarized our three different cases, and all of them are all kind of about that critical factor. So when our coefficient will be less than our critical factor, when our coefficient is equal to it, and when our coefficient is greater than it.